Welcome back, and here is lesson number 6, still on the task of implicit differentiation. In this question, this is now a typical examination question. It says find the points on the graph of x squared plus 4xy plus 3x squared y squared equals 4 at which the tangent is vertical. So find the points on the graph of this relation or of this equation at which the tangent is vertical. And part B says to determine the equations, it could be one or it could be more, of the tangent to the curve at the point where the value of x is -1. All right. So here is another problem where it is a lesson in the sense that we are learning some tricks on how to go about these questions. Otherwise, this question would appear under the playlist of problem set. All right. So let's see how we go about solving this question. Okay. So let's see how we solve this question. Here is the relation or the equation that we've been given. We want to find a point on the function. Notice that this is a relation and it's not a function. We can refer to it as an equation, but we can't refer to it as a function because it would fail the vertical line test. I believe I've sketched the graph somewhere, but we'll look at that later. So the first part is to find the coordinates of the points where the tangents are vertical. Now there may be one or there may be more, but we want to find all those points where if we draw a tangent to the curve, it's going to be vertical. All right? So what is the approach we use here? The first thing we want to do, we are told that the tangent is vertical. Because of that, we know that the gradient of the tangent is infinite. That is to say that around that region, the curve is kind of vertical like that, right? So we know that the gradient of that tangent must be infinite. So that is a point we must carry with us. The second thing we need to remember, so because of the first point there, we find the gradient of our function there, and then we will equate it to infinity. Because at the point we are discussing where the tangent is vertical, the gradient of the tangent must be the gradient of the function. So if we can't find the gradient of the function, we will equate that to the gradient of the tangent, and that should be infinite. All right, point number 3, we will use this equation to find the desired coordinates of the point on the function. Okay, now, so that is how the graph looks like. So effectively, the points where the tangent is vertical, where the gradient of the tangent is infinite, meaning the tangent is vertical, would have to be this point here. Okay, you can see that point there, or another point is right there. Okay, so we are going to find the coordinates of those points. What's the x coordinate and what's the y coordinate of that point? All right, let's move ahead and do it. So first thing is to differentiate that implicitly. If we differentiate that, I think now we can move a bit faster. So differentiating x squared gives me directly. So if we differentiate x squared, we get 2x. If we differentiate 4xy, we should get 4x dy dx plus 4y. Right, so 4x, so keep x constant, differentiate that. So 4x dy by dx. Then we keep y constant and differentiate x, and that's going to give me 1. So therefore our answer is 4x dy by dx plus 4y dx by dx, which is just 1. All right, and then we move to the next one. We have, all right, so we move to the next one there. We'll have 3x squared, and then we differentiate that. So that's going to give me 2y dy by dx. So I have 6x squared y dy by dx. Okay, so 3x squared is constant, and then differentiate y squared there. We get 2y dy by dx, which is going to give me 6x squared y dy by dx. Now we keep y constant, so we have 3y squared. So we have 3y squared and differentiate x squared. If we differentiate x squared, we get 2x. And that should be the derivative of, should be equal to the derivative of 4, which is a constant. The derivative of a constant is 0, and so that should give me a 0 at the end there. All we are left with is to simplify. So simplifying this means collecting the like terms, but of course also this is 6x squared y, all right, and this is 6xy squared. Right, so if we combine those together, we end up with dy by dx is that, or if you like, you can say dy by dx is the negative of all that, and that is our derivative of the function. So this is the equation we would use to find the gradient of that curve we had there. Anywhere really, we can find the gradient at any point on the curve that we've seen. All right, next, what we want is to find the coordinates of the points where the gradient is where the tangent is vertical. If the tangent is vertical, then we are saying that our gradient, which we have found here, must be infinite, right? So the tangent is vertical, so the gradient must be infinite, which means our derivative must also be infinite, like that. Okay, so I'm going to remove that and put its equivalent, which is that expression we found in the first part there. So replace that with its real value there. And now we reason that the only way this fraction here can be infinite is that the denominator there is 0. And therefore, 3x squared y plus 2x must be equal to 0. And if we factorize that, we'll get x. See, x is here and is also there, so we can factorize x out. So x is 0, or x is negative 2y, negative 2 over 3y, like that. So we now have some potential values of x. We want to know the values of y. We start by substituting x equal to 0 into the function to find the potential value of y. But if we substitute x here, that's 0, that's 0, and that's 0, and that is to say the left-hand side is going to be 0 equals 4, which is not possible. We can't have 0 equals 4, which is to suggest that there is no value of y for which x is 0. So x cannot be equal to 0. All right, we've substituted that. We show that x cannot be equal to 0, so it must be that all our values will come from here, from this value of x. In fact, what I'm going to do is to find the value of x first, then find the value of y. So I'm going to make y the subject of the formula there. It doesn't matter. I can put this here and find the value of y here, and find the value of y, and then use that to find the value of x. But instead, I'm going to make y the subject of the formula there, so that I replace y values with x like this. Substituting y is 2 over 3x. Effectively, what I've done is I've made y the subject there, right? So that it is y that I am substituting instead of x. So if I do that, then I will be substituting y. Where there is y, I'll remove it and put minus 2 over 3x. And if I do that, then I have x squared. If I substitute the values of y there, I will get, I think I have simplified this. So it's 4x times that. I'm substituting for y. Then we have 3x squared, and I'm substituting minus 2 over 3x and squared, and this should be equal to 4. Right? If you simplify this, you can see this x disappears with that. All right? And x squared disappears with x squared. This is going to be squared, and I'll have here 4 over 9. So 4 is 12 over 9. So x squared and x squared will have cancelled. If we simplify this in short, try it out. If we simplify this, we will get that x is 16 over 3, and when you look for the square root of that, you'll find that x is plus or minus root of 4 root 3 over 3. Okay, so you'll get 4 over root 3, and then you multiply the top and bottom by root 3 to rationalize the denominator, and this is what we get for values of x. So we now know the coordinates of x at which the tangent is going to be vertical. Since we know the values of x, the question was to find the coordinates of those points rather than just the x value. So we need the coordinate, meaning we also have to find the y values. So all we need to do now is to substitute the values of x in this formula. We don't have to go back there now. We can substitute them right here, okay? So when x is positive 4 root 3 over 2, what's the value of y? And when x is negative 4 root 3 over 3, what's the value of y? So if we do that, we get that the values of y are plus or minus root 3 over 6. So therefore, the coordinates of the required points must be positive 4 root 3 over 3, comma, negative root 3 over 6, and the next one will be negative 4 root 3 over 3 and positive root 3 over 6, like that, okay? I believe I've sketched this somewhere. There you go. And so one of the points has a coordinate, so we are saying the one with x value positive must be there. So this is just slightly over 2, if you check it out. And the y coordinate is negative. So you can see the y coordinate is going to be negative there, right? And the other one is this one where the x coordinate is negative, just beyond negative 2. And the x coordinate is going to be positive, just above 0, okay? So we have found the coordinates of the points on this, of that equation where the tangent is vertical. Okay, part B of the question was to find the equation of the tangent at the point where x is negative 1. So there is a point on this graph where x is negative 1 here. We want to know the tangent, we want to find the equation of the tangent there and the equation of the tangent on the lower end. Let's just show it here. So here we go. So we want to find the equation of the tangent at the point where the value of x is negative 1. So if we go to the point where the value of x is negative 1, which is somewhere there, the values of y there are, one of them is that point there. Okay, so there are those 2 points, one is at the bottom and one is at the top. So both points have an x coordinate of negative 1. What are the equations of the tangent? So we have 2 points with the x value of negative 1. We want to know the equation of the tangent at this point and the equation of the tangent at that other point. All right. So we know that this has a negative gradient. This one has a positive gradient. We'll need to find those gradients, right? Okay. So substituting our values, we substitute our values into the relation there. We already know, so if we substitute x is negative 1 into the function, we will get the value of the values of y. Substituting that, negative 1 here, we get 1. Now substitute negative 1 there, we get minus 4y. Substitute it there, we get plus 3y squared equals 4. And if you rearrange that quadratic, we get that. And if we solve that by, use the formula, for example, we will get that y is negative 0.54. So that must be referring to this one, which is negative 0.54. It was actually negative 0.535 something, rounded off to negative 0.54. And the other one, which is this one, turns out to be approximately 1.87. It was 1.868. All right, so 1.87 approximately. So those are the y values for that x value. So we know the coordinates of that point and that point as being negative 1, comma negative 0.54 and negative 1, comma 1.87. I've taken the liberty to name those points A and B. So the coordinates of point A and the coordinate of point B are given. So we know where the tangent is going to pass. We also can use these coordinates now to find the gradients at their respective point. Okay, so we know the equation of the gradient, all right? And now we know the coordinates of the points A and B. We can now go ahead and find the equation of the tangent through these 2 points, okay? We know the coordinates of point A. The next thing we need to know is what the gradient is at point A and the gradient at point B. So to find the gradient at A, we need to substitute these coordinates into the gradient function. We already found the gradient function as that. So if we substitute these coordinates, negative 1, 1.87 into this equation, we find the gradient at point A. I've used a calculator to do this. If you do so, you should find by simply substituting the value of x and the value of y in here, you should be able to get that the gradient at that point is approximately 2.15. All right, and now since we know the gradient and we know the coordinates, we can find the equation of the line that passes through point A. What we need to do is to make use of our knowledge that if we are given the coordinates of point A, say A, comma B. Those are the coordinates of point A. And we also know the gradient of the line. If we know the gradient, then we can choose another point, let's call it point M or X, whatever, and give it coordinates X, Y, so that these 2 points are on the line. If this is the case, then we can reason that the gradient M here must be equal to change in y, so I'm going to say y minus b, that's like y1 or y2 minus y1 over x2 minus x1, which is going to be x minus a, so I can write this as x minus a like that. And then what I want to do is to have this as the subject of the formula, so I'll write y minus b is always equal to m into x minus a like that. And so my suggestion to students is usually to keep this in mind, so you don't have to first look for the value of c, look for using the y is equal to mx plus c, and so first of all look for the value of the constant c, then substitute it back to find the equation of the line. You can do all that in one step if you can remember this relationship, okay? So keeping this relationship in mind, that is, take y, subtract the y coordinate, so subtract 1.87 must be equal to the gradient, our gradient is 2.5, into x minus the x coordinate, which is -1 there. And already that is the equation of the tangent to the curve. Let's do that quickly. Keep this here in mind, that's what I'm using. That gives me 2.15 is what I get using a graphical display calculator. And so because we know the coordinate and we know the gradient, we can now say that y minus 1.87 must be equal to the gradient, which is 2.15, into x minus the x coordinate, like that. And this is actually the equation of the line. If you simplify that, you should get y is 2.15x plus 4.02. So this is approximately the value of, this is the equation of the tangent to the curve at point A. That's the equation of the line that just kisses the function at A like that. Okay? Similarly, we can find the equation of the tangent at point B by doing practically the same thing. First thing is to use those points on the gradient function to find the gradient at point B. So the gradient at point B is going to be, if we substitute these values here, x and y, you get the gradient to be approximately -0.812 using a graphical display calculator. All right, and since we now have that and we know the coordinates of the point where it touches the function, we can use that to find the equation of the line using the same method. So y minus the y value there must be equal to the gradient, which is this, into x minus the x value there. If you rearrange that, you should get that the equation of this line is going to be y is -0.812x minus 1.35, okay? And that is how this line would look. Please try to sketch this relation or equation on GeoGebra or use relations in your calculator to try and sketch this relation, and then draw this the equation of this line and see if it really is the tangent at the point where x is -1. You should find that it is the same. All right, so this is how we answer this question. I hope you're able to understand. Again, remember to let me know if you need any clarification. Thank you very much. I'll see you in the next video. After this, we'll spend a bit more time now looking at questions examination type questions that come around this area. This is really it. There is nothing more to it. The only difference now is that the function that you're given may contain trig terms or exponential terms or logarithmic terms, but effectively the way you differentiate remains the same. Thank you, and see you in the next video.